Hi, so let's take a minute and look through a couple simple gravity problems. Um, so these are good examples of the kinds of problems you might encounter, and I just wanted to make sure that you had a solution where it's talked through working the problem, in addition to just having it worked out on paper. So this first question is asking us to find the speed and period of the International Space Station. So give ourselves a little cartoon of what's going on. We have the Earth, and the International Space Station is in low Earth orbit. If I can draw a circle here. Around it at some height, and that height is about 400 kilometers. And so we want to find the speed and the period for this orbit. So this question starts like a lot of these questions. If we sum the forces in R, we know that's going to be equal to the mass times the centripetal acceleration, the mass of the space station. Give ourselves a little more detail here. So here's our space station. This is the Earth. This would be traveling at some v. Add in also a vector to indicate the centripetal acceleration. As well as a vector to indicate the force. So this, in this case, this would be the force of gravity that's providing the centripetal acceleration. Better picture. And so the force of gravity, gmm over r squared. Now the r in this case is going to be the radius of the Earth plus the height, but let's just leave it as r for now. And this is going to be equal to the mass of the International Space Station times the centripetal acceleration, which we can write as v squared over r. And so notice a couple things are going to cancel out. This factor of mass cancels of the space station, so it doesn't matter the mass of the space station because it appears on both sides. And we'll also lose a factor of r that appears on both sides. And so we have something that says that the speed would be equal to the square root of g, mass of the Earth, big G, mass of the Earth, over r. And really this is big G, mass of the Earth. This is the radius of the Earth plus the height in the denominator. So let's put those numbers in and see what we get. So remember, big G is actually very small, 6.67, 10 to the minus 11 newtons meters squared per kilogram squared. The mass of the Earth is very large, 5.98, 10 to the 24 kilograms. And this radius, so the radius of the Earth, 6.38 times 10 to the 6 meters. And then we're going to add to that the height. The height was 400 kilometers, so 400 times 10 to the third meters. So we have everything in our base units. You crunch these numbers, you'd find that the speed is about 7.67 times 10 to the third meters per second, i.e. it's about 7.7 kilometers per second, which is pretty wild. It's definitely a lot faster than what we're accustomed to when we were talking about, blocks and cars and stuff moving. This is a whole different ballgame. 8 kilometers a second. And this is reflective of the fact you can have speeds like that in space where, there isn't any air to have any drag or anything like that. And really, this is the speed that's required to have an orbit at that height, a circular orbit at that height. And that's the speed. And then the other thing that we're looking for would be the period. So the period, remember, is related to the speed given by the circumference of the orbit over the speed. And I should mention here, we're assuming that this is a circular orbit, which makes this simpler to solve. And we'll do that for a lot of these simple questions. In general, the orbits are elliptical, and we'll see that in simulation and stuff, and you can see that in Kepler's laws. But for these kinds of problems, we just assume that it's a circle. And so now that we know the speed and we know the radius, we can put those ingredients together and find the period. So I'm kind of out of room right here. Let me write it over here. So the period will be the circumference over the speed. And so for us, this will be 2 pi times Earth plus the height, 403. And that's all going to be divided by the speed. And when we crunch these numbers, we find that the period is going to be about 5.5 times 10 to the 6 seconds. It's a lot of seconds. It's a little bit hard to visualize that. So if we divide by 60 seconds, this tells us that period is 92 and a half minutes. So in other words, it takes the International Space Station about 92 and a half minutes to circle the Earth. Which is pretty cool. And this is a good example of, one of these kinds of simple orbit problems. So let's take a look at this second question. Derive the radius of a geosynchronous satellite orbit. So geosynchronous satellite, if you don't know what that is a satellite. So as you know, the Earth is rotating on its axis, which it does once per day. And a geosynchronous satellite would be a satellite that's parked such that it's orbiting the Earth once per day as well. So you can think of this as looking at the same spot on the equator once per day, or all the time. It's synced up with the orbit, with the rotation of the Earth, in other words. So we can think of this as we need to find the radius for this orbit given that period that it orbits the Earth once a day. So instead of solving for the speed and the period like we did in the last question, we're going to solve for the radius in this case. So let's put in all our ingredients here. So the satellite has some velocity at that. Oh, this is actually a little misleading here. This will be the radius of the orbit, and then the radius of the Earth would of course be the same. What else? Let's put a vector in here to indicate that this is the force of gravity. It's providing this centripetal acceleration, and let's also put in a vector just to reinforce the idea that that centripetal acceleration is pointing towards the center of the Earth. Okay, so we can start from scratch. Again, if you sum the forces in R, that's going to be GMM, the mass of the Earth, the mass of the satellite, over the radius squared. That's the radius that we're looking for. this is going to be equal to the mass of the satellite times the centripetal acceleration, which we know we can write as v squared over r. So again, some stuff is going to cancel here. The mass of the satellite drops out, and we'll lose a factor of r. And now in this case, we're going to make use of the period. We know the period. And so let's substitute in for v. So v is equal to the circumference over the period. So let's put that in here. Get rid of the stuff that we've dropped, and we'll see that this is equal to then 2 pi r over t, capital T is the period, that quantity squared. So notice we're trying to get r by itself, so we can do some algebra here, move some stuff around. Let's multiply by a factor of t squared to put that over here. Divide by a factor of 4 pi squared. And then that would mean that this whole thing is equal to r cubed. So since we're looking for r would then equal the cubed root of gme, mass of the Earth, times t squared over 4 pi squared. So it's a little bit weird to do cubed roots. I would recommend, or I tell students, make sure you can figure out how to do that on your calculator should you need to do that in an exam, say. It can be a little bit of a combination of buttons or kind of tricky. So let's put in our numbers and see what we get. G, 10 minus 11. The mass of the Earth. The period, so we need to put the period in seconds. So we know what it is in hours. And we also know that in an hour, there is 3,600 seconds, 60 times 60. So that'll give us the period in seconds. And remember, we have to square this quantity. And then this whole thing will be over 4 pi squared. And then that whole mess is to the 1/3. We take a cube root of that. And so when you crunch your numbers, you'll find that this radius would give you, or this calculation would give you 4.2 times 10 to the 7 meters, which may not really mean that much, or it's a difficult, it's a big number, but we can compare this to the radius of the Earth, which is 6.38 times 10 to the 6, and you would see that this radius, so maybe we'll call this like radius of, I don't know, geosynchronous or something, is about 6.6 times the radius of the Earth. So in other words, my picture here is not very accurate, not very well to scale. Compared to the radius of the Earth, this if I can draw like a brace here, this would need to be, about 6.6 times the radius of the Earth. So I can try and draw like a slightly more to scale diagram. So it's a lot farther than, say, the International Space Station, which is in low Earth orbit, where that was 400 kilometers, and this is 6 times the radius of the Earth. 7 times the radius of the Earth. Anything else that I wanted to mention? We could also look at things like the speed, which is simple to get now that we have the radius, 2 pi r over the t, over the period. So we know the period and we know the speed, or we know the radius. Let's just do that quick. And you crunch this number and you find that this is about 3 kilometers per second. So another, in contrast to the ISS, this is both slower uh, than ISS as well, and much farther away. So this is an example of a question where instead of solving for the speed, we were looking for the radius. And you can imagine, different questions, solving for the mass, solving for any of these things. I think you'll find once you practice a few of these, uh, they're not so bad. It's mostly just, getting familiar and comfortable with the algebra to solve these kinds of problems. So hopefully this helps as you're working through this material.